Hello and welcome to the Sleepy Physicist. Tonight, we're embarking on a journey to one of the most profound mysteries in the universe. A question that touches the very fabric of reality itself. If you're settling into bed, curling up on the couch, or simply finding a quiet moment to wonder about the cosmos, you've come to the right place. This is where physics meets philosophy, where hard science dissolves into gentle contemplation. Now, I do hope this exploration isn't so fascinating that it keeps you awake, but if it does, at least you'll drift off, with some truly cosmic thoughts swirling through your mind. Before we begin, if you enjoy these slow journeys through the deeper mysteries of physics, I'd be grateful if you tapped the like button, subscribed, or simply left a comment telling me where in the world you're listening from tonight. There's something oddly comforting about knowing that somewhere, whether it's midnight in Manchester or 3 a.m. in Tokyo, curious minds are pondering the same eternal questions. So take a deep breath, settle in, and let's begin our gentle voyage into the shocking connection between entropy, light, and the ultimate speed limit of existence itself. Here's something that might surprise you. Every single photon of light that has ever existed, from the first moment after the Big Bang to the gentle glow of your bedside lamp right now, travels at exactly the same speed. Not approximately the same speed, exactly. And nothing, absolutely nothing in the universe can go faster. But here's the truly mind-bending part. This isn't just some arbitrary cosmic speed limit. This fundamental boundary is intimately connected to entropy, the measure of disorder in the universe, and it reveals something profound about the nature of time itself, causality, and why reality has the structure it does. Tonight, we're going to uncover why the universe has a speed limit at all, why that limit happens to be the speed of light, and how this connects to one of the most fundamental principles governing everything, from your morning coffee cooling down to the eventual heat death of the cosmos. It's a story that begins with the deepest symmetries of space-time and ends with a revelation about the very nature of existence. Picture this: you're holding a warm cup of tea on a cold evening. As you sit quietly, you can almost feel the heat flowing from the cup into the surrounding air. The tea cools, the room warms ever so slightly, and something irreversible has happened. Entropy has increased. But what does this have to do with light speed more than you might imagine? Let's start with something beautifully simple, yet profound. Light moves at approximately 300,000 kilometers per second in a vacuum. We call this speed c, and it appears everywhere in physics, from Einstein's famous irreversibility to the equations that govern quantum mechanics. But here's what's truly remarkable. This speed isn't really about light at all. It's about the fundamental structure of space-time itself. Imagine space-time as a vast fabric woven from the threads of space and time. This fabric has certain properties, certain rules about how information can flow through it. The speed of light is actually the maximum speed at which any cause can produce an effect, the ultimate rate at which information can travel from one point to another. It's the speed of causality itself. Now, you might wonder, why should there be a speed limit at all? Why can't information travel instantaneously across the universe? The answer lies in a deep principle that governs all of reality, the preservation of causality. If information could travel faster than light, something extraordinary and disturbing would happen. Effects could precede their causes. Let me paint you a picture of what this would mean. Imagine you could send a message faster than light to a friend on a distant star. Due to the strange effects of relativity, depending on how you and your friend are moving relative to each other, Your friend might receive your message before you sent it, from their perspective. They could then send a reply that reaches you before you even decided to send the original message. You could, in principle, receive an answer to a question you hadn't yet asked. This isn't just inconvenient, it would shatter the logical structure of reality itself. The universe would become a place where effects routinely precede causes, where the future could influence the past in endless loops of contradiction. It would be like trying to read a book where every sentence referred to events described in sentences that came later, creating an infinite regress of meaning. The speed of light, then, isn't just a speed. It's a guardian of logic, a cosmic boundary that preserves the coherent flow of cause and effect throughout the universe. But there's something even deeper here, something that connects this speed limit to the arrow of time itself. Enter entropy, that mysterious quantity that always increases in isolated systems. Entropy is often described as disorder, but that's not quite right. It's better thought of as the number of ways a system can be arranged on a microscopic level, while looking the same on a macroscopic level. When your tea cools, the heat energy spreads out among more and more air molecules, creating more possible arrangements of that energy. Entropy increases, and time, in a very real sense, moves forward. But here's where it gets truly fascinating. The speed of light and the increase of entropy are not separate phenomena. They're intimately connected through the fundamental physics of information. Every physical process, from the collision of particles to the cooling of your tea, involves the flow of information through space-time, and that information cannot travel faster than the speed of light. Think about it this way. When a hot object cools down, information about its thermal state must propagate outward, informing the surrounding environment about the heat that's being released. This information travels at the speed of light, carried by electromagnetic radiation, photons streaming away from the hot object into the cooler surroundings. The rate at which entropy can increase is fundamentally limited by how quickly this information can spread. This creates a beautiful symmetry in the universe. The speed of light sets the rate at which causes can create effects, and the increase of entropy sets the direction in which time flows. Together they create the temporal structure we experience, a universe where the past influences the future, but not the reverse, where heat flows from hot to cold, but not the reverse, where complexity can increase, but the overall trend is toward equilibrium. Consider the sun, that great nuclear furnace that powers life on Earth. Deep in its core, hydrogen nuclei fuse into helium, releasing tremendous amounts of energy. This energy begins as high-frequency gamma rays, but as it travels outward through the dense solar material, it gets absorbed and re-emitted countless times, gradually losing energy and increasing in wavelength. By the time it reaches us, it's become the gentle visible light that warms our faces and powers photosynthesis. This journey from the sun's core to your eyes takes about 100,000 years for the energy, but only 8 minutes and 20 seconds for the final photons that escape the sun's surface. And here's the remarkable thing. Those photons carry entropy. They represent a flow of disorder from the sun into the vast cold of space. The sun is decreasing its entropy by converting hydrogen into helium, but it's increasing the entropy of the universe by radiating energy into the cosmic background. Every photon that leaves the sun and travels to Earth is participating in the universe's grand march toward maximum entropy. The light that allows plants to grow, that powers weather systems, that ultimately makes life possible, is also a manifestation of time's arrow. entropy's relentless increase toward equilibrium. This brings us to one of the most profound insights in modern physics. The speed of light doesn't just limit how fast things can move, it limits how fast the universe can evolve toward its ultimate state of maximum entropy. It sets the pace of cosmic evolution itself. But why should there be such a speed at all? Why should the universe have this fundamental limitation? The answer takes us into the deepest realms of theoretical physics, to principles so fundamental that they shape the very existence of space and time. At the heart of modern physics lies something called gauge symmetry. Don't worry about the technical details. The important point is that the laws of physics remain the same under certain transformations. If you're an electron, for instance, you can't tell whether someone has rotated your quantum mechanical phase by some arbitrary amount. The physics looks exactly the same. This symmetry, this fundamental sameness under transformation, is what gives rise to the electromagnetic force, and with it the existence of light itself. Photons, the particles of light, are massless precisely because of this symmetry. And massless particles, by the laws of relativity, must travel at the speed of light. They cannot go slower, and they cannot go faster. They exist in a realm of pure motion, pure information transfer, travelling always and only at the cosmic speed limit. Here's where it gets even more beautiful. Particles with mass like electrons or protons or you and me can never reach the speed of light. As they approach this cosmic speed limit, something remarkable happens. Their resistance to acceleration increases. It becomes harder and harder to make them go faster. To actually reach the speed of light would require infinite energy, which is impossible. This creates two realms in our universe. The realm of matter, which always travels slower than light, and the realm of pure energy and information, which always travels at light speed. Nothing can cross between these realms. It's as if the universe has drawn a fundamental line, separating the material from the purely energetic, the substantial from the informational. And this boundary, this cosmic speed limit, is what preserves the logical structure of reality. It ensures that information flows in a consistent direction through space-time, that entropy can increase in an orderly fashion, that the past influences the future, but not the reverse. It's what makes the universe comprehensible, what allows for the existence of cause and effect, memory and anticipation, growth and decay. But there's something even more mysterious here, something that challenges our deepest intuitions about reality itself. Modern physics suggests that the three-dimensional world we experience might be an illusion, a projection from a two-dimensional boundary, like the shadows on the wall of Plato's cave. This is called the holographic principle, and it emerges from studying black holes, those ultimate laboratories where entropy and the speed of light meet in the most extreme conditions imaginable. When matter falls into a black hole, it seems to disappear into the interior. But quantum mechanics tells us that information cannot be destroyed. So where does it go? The holographic principle suggests that all the information about the matter that falls in is encoded on the black hole's surface, its event horizon. The three-dimensional interior might be nothing more than a way of organizing information that actually lives on the two-dimensional boundary. This principle has profound implications. It suggests that everything in the universe, every particle, every force, every interaction, might actually be encoded on a distant two-dimensional surface. We might all be projections, shadows cast by information living on the boundary of space-time itself. And the speed of light, the cosmic speed limit, might be what determines how quickly information can be processed on this cosmic boundary, how rapidly the holographic projection we call reality can evolve. This isn't just abstract theorizing. Recent advances in machine learning have confirmed something remarkable. When artificial intelligence algorithms are trained to identify the direction of time's arrow in physical systems, they consistently identify entropy production as the key factor. The algorithms effectively rediscover the second law of thermodynamics on their own, confirming that the increase of entropy is indeed the fundamental signature of time's passage. And all of this is intimately connected to the speed of light, to that fundamental cosmic boundary that prevents information from traveling faster than causality itself. Every time entropy increases in your cooling cup of tea, every time a photon carries energy from the sun to a leaf, every time a thought forms in your brain through the complex dance of neurons and neurotransmitters, you're witnessing the interplay between information, entropy, and the cosmic speed limit. The universe, it seems, is fundamentally about information processing, about the flow of data through the fabric of space-time at the ultimate rate permitted by the laws of physics. We are all part of this vast computational process, this cosmic algorithm that transforms low entropy initial conditions into the rich complexity we see around us, all while marching inexorably toward maximum entropy, toward the heat death that awaits all isolated systems. But don't let that cosmic perspective diminish the wonder of this moment. Right now, as you listen to these words, photons are streaming from your screen or reflecting off this page, carrying information about these ideas into your eyes, where they're converted into neural signals that travel through your brain at speeds far slower than light, but fast enough to weave these concepts into the fabric of your understanding. You are a temporary eddy in the universe's flow toward equilibrium, a brief organization of matter and energy that can contemplate its own existence, ponder the cosmic speed limit, and wonder at the deep connections between entropy, information, and the nature of time itself. And that capacity for wonder, that ability to step outside the flow of entropy for a moment and marvel at the cosmic dance, might be the most remarkable thing of all. But our journey into this cosmic mystery is just beginning. We've explored the fundamental connection between the speed of light and entropy, seen how they work together to create the arrow of time and preserve causality. But there are even deeper questions waiting to be explored. How does this cosmic speed limit connect to the quantum realm, where particles seem to influence each other instantaneously across vast distances? What happens at the very boundaries of space-time itself, where our understanding of physics begins to break down? And perhaps most intriguingly of all, if our universe is indeed bounded by the speed of light, if information processing is fundamentally limited by this cosmic speed limit, what does that tell us about the nature of consciousness itself? Are we, in some sense, computational processes running on the cosmic computer that is reality, our thoughts and experiences emerging from the complex flow of information through space-time? These questions lead us to even more profound territories, to places where physics meets philosophy, and where the boundaries between observer and observed begin to blur. In our next exploration, we'll delve into something that challenges our very existence on this planet, a cosmic coincidence so improbable that it makes you wonder whether we're living in a universe fine-tuned for our survival. The moon's terrifying secret. Why life on Earth shouldn't exist. Until then, rest well, and remember that every photon of starlight that has travelled across the cosmos to reach your eyes tonight has done so at exactly the same speed, carrying with it the story of entropy's increase and time's passage. A gentle reminder that you are part of something vast, mysterious, and beautiful beyond measure. These questions lead us deeper into the quantum realm, where the relationship between information, entropy, and the speed of light becomes even more mysterious. You see, quantum mechanics presents us with what Einstein famously called spooky action at a distance, a phenomenon that seems to mock our cosmic speed limit while somehow preserving it at the same time. Imagine two particles that have become entangled, their quantum states forever linked, no matter how far apart they drift through space. When you measure one particle and find it spinning clockwise, its entangled partner, even if it's on the other side of the galaxy, will instantly be found spinning counterclockwise. This correlation happens faster than light could travel between them. It's as if the universe maintains a hidden communication network that operates outside the normal rules of space-time. But here's the beautiful paradox. While these quantum correlations appear to violate the speed of light limit, they actually preserve it in the most elegant way possible. You cannot use entanglement to send usable information faster than light. The correlations only reveal themselves when the measurement results are compared using conventional, slower-than-light communication methods. It's like having a pair of magic coins that always land on opposite sides when flipped simultaneously, but neither flipper knows whether they were first or second until they call each other on the phone. This quantum mystery connects to entropy in a profound way. When particles become entangled, information about their individual states becomes increasingly diffuse, spread out across the quantum system in ways that make it impossible to extract complete knowledge about either particle alone. The entropy of the entangled system remains constant, but from any local perspective, information appears to be lost, inaccessible, hidden in the quantum correlations that bind the particles together. Think of it this way: entropy isn't just about energy spreading out or systems becoming more disordered. At its deepest level, entropy is about information becoming inaccessible. When your coffee cools, it's not that the thermal energy disappears. Rather, the information about which molecules have high kinetic energy becomes scrambled among so many particles that it's practically impossible to track. The information is still there in principle, but it's beyond our ability to access or use. This perspective transforms our understanding of time's arrow. The universe isn't really losing information as entropy increases. Instead, information is becoming increasingly entangled, woven into quantum correlations so complex that recovering it would require resources beyond what's practically available. The arrow of time emerges not from true information loss, but from information becoming buried in quantum complexity and the speed of light. It sets the rate at which these quantum entanglements can form and evolve. Information cannot become inaccessible faster than the cosmic speed limit allows. Even in the quantum realm, causality is preserved, time's arrow is maintained, and the fundamental structure of reality remains intact. But let's step back from these abstract quantum mysteries and consider something more tangible, more connected to your daily experience. Right now, as you listen to these words, your brain is processing information at a staggering rate. Billions of neurons are firing, creating patterns of electrical and chemical activity that somehow give rise to your conscious experience of understanding these concepts. Yet for all its computational power, your brain operates far slower than the speed of light, Neural signals travel at perhaps a few hundred meters per second, crawling compared to light's blazing 300 million meters per second. This seems like a limitation, but it's actually essential to your existence. If neural signals traveled at light speed, your brain would become a chaotic mess of simultaneous activations, with no time for the careful, sequential processing that creates coherent thought. Your consciousness emerges from this slower-than-light dance of neural activity, from patterns of information flow that unfold over milliseconds and seconds rather than nanoseconds. You are a creature of biological time, not cosmic time, living in the spaces between photons, thinking thoughts that emerge from the careful orchestration of matter moving far below the universal speed limit. This raises a fascinating question. What does it mean to be conscious in a universe bounded by the speed of light? Your thoughts, your memories, your sense of self, all emerge from information processing that respects the cosmic speed limit. Every decision you make, every emotion you feel, every moment of awareness is shaped by the fundamental fact that information cannot travel faster than causality itself. Consider memory. When you remember a childhood summer day, you're not accessing some fixed record stored in your brain like a video file on a computer. Instead, your neurons are recreating patterns of activity similar to those that occurred when the memory was first formed. This recreation takes time, requires energy, and increases entropy. The act of remembering is itself a thermodynamic process, converting organized neural energy into heat while extracting information from the complex web of synaptic connections in your brain. And here's something truly remarkable. The speed of light enters into this process in subtle but fundamental ways. The biochemical reactions that power neural activity, the flow of ions across cell membranes, the release of neurotransmitters across synaptic gaps. All of these processes are ultimately governed by electromagnetic forces that propagate at light speed. The atoms in your neurons interact through photon exchanges, virtual particles of light that mediate the electromagnetic force binding matter together. You are, in a very real sense, a creature of light, held together by electromagnetic forces, thinking thoughts that emerge from light-speed interactions between atoms, living a life bounded by the cosmic speed limit, even in your most private mental moments. The photons that carry the electromagnetic forces binding your neurons together are the same type of particles that carry starlight across the cosmos, that bring you the warmth of sunlight on your face, that allow you to see the words on this screen. This connection between consciousness and the cosmic speed limit leads to some profound philosophical implications. If our thoughts and experiences are fundamentally limited by the speed of light, what does that tell us about the nature of consciousness itself? Are we, in some sense, computational processes running on the cosmic computer that is space-time? Our awareness emerging from patterns of information flow that respect the universe's fundamental speed limit? Some scientists and philosophers have suggested that consciousness might be understood as a way that the universe becomes aware of itself, a process by which matter and energy, organized in sufficiently complex patterns, develops the capacity for self-reflection. If this is true, then the speed of light isn't just a physical limit, it's also a cognitive one, setting boundaries on how quickly conscious systems can process information about their own states and their environment. This perspective connects consciousness to entropy in a beautiful way. Your awareness might be understood as a temporary decrease in local entropy, a brief organization of matter and energy into patterns complex enough to sustain self-reflection. But this local decrease comes at the cost of increased entropy elsewhere, as your brain converts organized chemical energy into heat while generating thoughts and experiences. You are, from this thermodynamic perspective, a dissipative structure, a temporary whirlpool in the universe's flow toward maximum entropy, like a flame that maintains its shape while consuming fuel and producing heat. Your consciousness maintains its coherence while constantly processing energy and information, adding to the universe's overall disorder, even as it creates moments of local order and awareness. But don't let this reductionist view diminish the wonder of consciousness. The fact that patterns of matter and energy, organized according to the laws of physics and bounded by the speed of light, can give rise to awareness, to the capacity for wonder and reflection, to the ability to contemplate the very cosmic principles that govern our existence. This is perhaps the most remarkable phenomenon in the universe. And it's happening right now in your brain as you process these ideas. Neurons are firing in patterns shaped by billions of years of evolution, creating thoughts that span from the quantum realm to cosmic scales, all while respecting the fundamental speed limit that governs reality itself. The same principles that prevent faster-than-light travel also make possible the complex information processing that gives rise to your moment of understanding. This brings us to one of the most profound questions in all of science. Why does the universe seem so perfectly calibrated for the existence of complexity, of life, of consciousness? The speed of light, the laws of thermodynamics, the fundamental constants of physics, all appear to be fine-tuned with extraordinary precision to allow for the emergence of organized structures like stars, planets, and living beings. If the speed of light were much faster, causality would become muddled, and the coherent evolution of complex systems would be impossible. If it were much slower, the universe would be a sluggish place, where information travelled so slowly that complex patterns could never form and evolve. The cosmic speed limit seems to be set at just the right value to allow for the emergence of complexity within the framework of entropy increase. Similarly, the relationship between energy and matter, encoded in Einstein's famous equation E=mc2, depends critically on the value of the speed of light. If c were different, the nuclear reactions that power stars would proceed at different rates, potentially making stellar evolution incompatible with the formation of the heavy elements necessary for life. The cosmic speed limit isn't just a constraint on motion, it's a fundamental parameter that determines the very possibility of complexity in the universe. This apparent fine-tuning has led some scientists to propose the Anthropic principle, the idea that we observe the universe to have the properties it does precisely because those properties allow for the existence of observers like us. In universes where the fundamental constants were different, where the speed of light or the laws of thermodynamics took other forms, there would be no conscious beings to observe and wonder about cosmic principles. But this raises an even deeper question. Are there other universes, other realities with different values of the fundamental constants? The concept of a multiverse suggests that our universe might be just one of countless others, each with its own physical laws, its own speed limits, its own relationship between entropy and information. In this vast ensemble of realities, we naturally find ourselves in one where the conditions allow for our existence. From this perspective, the speed of light and the laws of entropy aren't arbitrary features of reality. They're the inevitable characteristics of any universe capable of supporting the complex information processing structures we call life and consciousness. We exist in a reality where these principles take the forms they do precisely because those forms make our existence possible. Yet even if our universe is one of many, even if the cosmic speed limit and entropy's increase are just local features of our particular reality, they remain fundamental to our experience, to our understanding of what it means to exist as conscious beings in a physical universe. They shape every moment of our lives, from the way light brings us information about the world to the way our thoughts emerge from the thermodynamic processes in our brains. The speed of light connects us to the cosmos in the most intimate way possible. The photons that allow you to see these words left their sources at exactly the cosmic speed limit, carrying information across space and time to reach your eyes. Some of those photons might have originated in stars that died billions of years ago, their light only now reaching Earth after an epic journey across the expanding universe. When you look up at the night sky, you're seeing the universe as it was, not as it is. The light from distant stars and galaxies carries information about the past, about the state of the cosmos at earlier epochs, when entropy was lower, when the universe was younger and more organised. In a very real sense, looking into space is looking backward in time, and the cosmic speed limit is what makes this temporal vision possible. This temporal aspect of light connects us to the deep history of the universe, to the story of how entropy has increased over cosmic timescales. The cosmic microwave background radiation, the afterglow of the Big Bang itself, still bathes the entire universe in faint light that has been travelling for nearly 14 billion years. This ancient light carries information about the earliest moments of cosmic history, about the initial conditions from which all subsequent complexity has emerged. The universe began in a state of extraordinarily low entropy, with matter and energy distributed almost uniformly throughout space. Gravity, that weakest of the fundamental forces, was responsible for creating the first departures from uniformity, pulling matter together into the first stars and galaxies. As these gravitational structures formed and evolved, they created the conditions necessary for the complex chemistry that would eventually give rise to life. Throughout this cosmic evolution, the speed of light has served as both a constraint and an enabler. It has prevented the universe from evolving too quickly, allowing time for the gradual processes of stellar evolution, element formation, and planetary development. At the same time, it has enabled the flow of energy and information necessary for the emergence of increasingly complex structures. The story of cosmic evolution is intimately connected to the story of entropy increase and information flow, all governed by the fundamental speed limit that we call the speed of light. From the first moments after the Big Bang to the formation of the first atoms, from the birth of stars to the emergence of life on planets like Earth, every step in this cosmic journey has been shaped by the principles we've been exploring. And now, billions of years after those first photons began their journey through space, some of their descendants are reaching your eyes, carrying information about these deep cosmic principles into your consciousness. You are part of this vast story, a temporary organisation of matter and energy that has developed the capacity to understand its own cosmic context, to appreciate the fundamental principles that govern reality itself. But our exploration of these cosmic principles is far from over. We've seen how the speed of light and entropy work together to create the arrow of time, to preserve causality, and to enable the emergence of complexity. We've glimpsed how consciousness itself might be understood as a thermodynamic process, a way that the universe becomes aware of itself through patterns of information flow that respect the cosmic speed limit. Yet there are even deeper mysteries waiting to be explored, connections between these fundamental principles and the specific conditions that make life possible on our planet. Why does Earth exist in such a narrow band of conditions suitable for complex chemistry and biological evolution? What cosmic coincidences have conspired to create a world where consciousness can emerge and contemplate its own existence? These questions lead us to examine one of the most remarkable and potentially terrifying aspects of our cosmic situation, a celestial arrangement so improbable that its very existence challenges our understanding of cosmic evolution and planetary formation. The moon's terrifying secret: why life on Earth shouldn't exist. These questions about cosmic coincidences bring us to something even more mysterious, a phenomenon that exists at the very intersection of quantum mechanics and relativity, where the speed of light reveals new layers of cosmic strangeness. You see, there's something profoundly unsettling about how the universe processes information, something that suggests reality might be far more fragile and interconnected than we ever imagined. Consider what happens when information approaches the cosmic speed limit. In the everyday world, we're used to information travelling at comfortable human speeds. A whispered secret crosses a room in milliseconds. A text message reaches a friend in seconds. But when information travels at the speed of light, something extraordinary occurs. Time itself begins to dilate, space contracts, and the very fabric of causality stretches to its limits. Imagine you're a photon, born in the nuclear furnace at the heart of a distant star. From your perspective, something remarkable happens. Due to the effects of special relativity, your journey across millions of light years of space occurs in literally no time at all. From the moment you're created to the instant you strike a retina or a telescope mirror, zero time passes in your reference frame. You experience the entire universe as a single, timeless moment. This isn't just a curiosity of physics. It reveals something profound about the relationship between information, entropy, and consciousness. Every photon that has ever carried information across the cosmos has done so in its own eternal now, a timeless instant that connects the moment of creation to the moment of observation. The speed of light isn't just a velocity, it's a gateway to eternity, a realm where time ceases to flow and all of cosmic history becomes a single, unified experience. But here's where it gets truly mysterious. While photons experience timelessness, we conscious observers exist in the realm of flowing time, where entropy increases and memories form and fade. We are temporal beings trying to understand an atemporal universe, creatures of sequential experience, contemplating a cosmos where simultaneity is relative and causality is the only absolute. This creates a profound paradox at the heart of existence. The very light that brings us information about the universe, that enables our vision and powers our thoughts, exists in a realm completely alien to our temporal experience. We are beings of time trying to understand messengers from eternity, creatures whose consciousness emerges from slow biological processes, attempting to comprehend phenomena that occur at the ultimate speed of existence. And yet there's something beautiful about this cosmic arrangement. The speed of light creates a buffer zone between different scales of reality. At human scales, we experience a world where causality is clear, where past and future are distinct, where we can form memories and make plans. At cosmic scales, the universe operates according to relativistic principles that seem to defy common sense, but preserve the deeper logic of space-time. This buffer zone is essential for the existence of complex structures like living beings. If the effects of relativity were more pronounced at human scales, if time dilation and length contraction were everyday experiences, the delicate processes that sustain life would become impossible. The biochemical reactions in your cells, the electrical signals in your nervous system, the intricate dance of molecules that creates consciousness, all depend on having a stable temporal framework in which to unfold. The cosmic speed limit protects this stability while still allowing for the flow of information and energy that connects us to the larger universe. It's as if reality has multiple layers, each operating according to its own temporal logic, but all connected by the fundamental principle that information cannot travel faster than light. This multi-layered structure of reality becomes even more apparent when we consider how entropy manifests at different scales. At the quantum level, individual particles exist in superpositions of states, neither fully ordered nor disordered until observed. At the thermodynamic level, large collections of particles follow statistical laws that drive systems toward equilibrium. At the cosmic level, the expansion of the universe creates an ever-increasing arena for entropy to spread into. The speed of light connects all these scales, setting the rate at which information can flow between quantum and classical realms, determining how quickly thermodynamic equilibrium can be approached, governing the pace at which cosmic expansion can carry entropy into new regions of space-time. It's the universal conductor, orchestrating the symphony of existence across all scales of reality. But there's something even more profound lurking in the mathematics of space-time, something that challenges our most basic assumptions about the nature of reality itself. The equations of general relativity, Einstein's masterwork that describes gravity as the curvature of space-time, contain solutions that seem to violate everything we thought we knew about causality and the flow of time. These solutions, called closed time-like curves, represent paths through space-time that loop back on themselves, creating the theoretical possibility of time travel into the past. If such curves exist, you could, in principle, travel back in time and meet your younger self, creating all sorts of logical paradoxes and contradictions. Yet even these exotic solutions respect the cosmic speed limit in their own strange way. Any journey along a closed time-like curve must still follow the geometry of space-time, must still respect the principle that massive objects cannot exceed the speed of light locally. The universe seems to find ways to preserve causality even when space-time itself curves back on itself. Most physicists believe that some unknown principle, perhaps related to quantum mechanics or the nature of entropy, prevents closed time-like curves from actually forming in our universe. The cosmic speed limit might be part of a larger set of principles that maintain the logical consistency of reality, that prevent the universe from collapsing into paradox and contradiction. This brings us to one of the most mind-bending aspects of modern physics, the idea that space-time itself might have limits, boundaries beyond which our current understanding breaks down. Near black holes where gravity becomes so intense that it warps space-time almost beyond recognition, strange things begin to happen to the relationship between space, time, and information. The event horizon of a black hole marks a boundary where the escape velocity equals the speed of light. Beyond this boundary, not even light can escape the gravitational pull, but from the perspective of an outside observer, something remarkable occurs. due to gravitational time dilation, time appears to slow down near the event horizon, approaching a complete stop at the boundary itself. This means that from our perspective, anything falling into a black hole would appear to freeze at the event horizon, its image redshifted and dimmed, but never quite disappearing. The information carried by the falling object would become stretched across the black hole's surface, encoded in the subtle fluctuations of the event horizon itself. This is where the holographic principle emerges in its full glory. The three-dimensional interior of the black hole might be nothing more than a way of organizing information that actually lives on the two-dimensional event horizon. The speed of light, in this context, determines how quickly information can be processed on this cosmic boundary, how rapidly the holographic projection we call reality can evolve and change. If this principle applies to the entire universe, then everything we experience, every thought we think, every emotion we feel, might be a projection from information encoded on a distant boundary. We would be living in a cosmic hologram, unaware that our three-dimensional reality is actually a shadow cast by two-dimensional information processing at the edge of space-time. This perspective transforms our understanding of the speed of light from a simple velocity limit into something far more profound: the processing speed of the cosmic computer that generates our reality. Every photon that travels through space, every electromagnetic interaction that binds atoms together, every neural signal that creates consciousness, would be part of this vast computational process. And here's what's truly remarkable. Even if we are living in a holographic projection, even if our reality is generated by information processing on a distant boundary, the experience of existence remains just as meaningful, just as beautiful, just as worthy of wonder and contemplation. The love you feel for others, the awe you experience when contemplating the cosmos, the quiet satisfaction of understanding a difficult concept, all of these experiences retain their full significance regardless of the underlying computational substrate. In fact, the holographic principle might explain why consciousness seems to emerge so naturally from complex information processing systems. If reality itself is fundamentally informational, if the universe is at its deepest level, a vast pattern of data processing, bounded by the speed of light, then the emergence of conscious observers might be an inevitable feature of any sufficiently complex cosmic computation. This brings us back to the profound connection between entropy, information, and the arrow of time. In a holographic universe, the increase of entropy would represent the spreading of information across the cosmic boundary, the gradual filling of available computational resources with increasingly complex patterns of data. The second law of thermodynamics would become a statement about information processing capacity, about the limits of computation in a universe bounded by the speed of light. The arrow of time would emerge from the asymmetric boundary conditions of this cosmic computation, from the fact that the universe began with a simple, low-entropy initial state that has been evolving toward greater complexity and disorder ever since. We would be temporary patterns in this vast information processing system, brief organizations of data that have developed the capacity for self-reflection and wonder. Yet even in this computational view of reality, there remains something irreducibly mysterious about consciousness, something that seems to transcend mere information processing. The subjective experience of being aware, of having thoughts and feelings and sensations, appears to involve something more than just the manipulation of data even very complex data. This is what philosophers call the hard problem of consciousness, explaining how subjective experience arises from objective physical processes. Even if we can map every neural connection in the brain, even if we can simulate every aspect of brain function on a computer, the question remains, why should there be anything it's like to be conscious? Why shouldn't all this information processing occur in the dark without any accompanying inner experience? The speed of light might hold clues to this mystery. Consciousness seems to require a certain kind of temporal integration, a binding together of information from different sources into a unified experience. This integration takes time, and that time is ultimately limited by the speed at which information can travel through the neural networks of the brain. Perhaps consciousness emerges from a specific kind of information processing that occurs when signals traveling at various speeds, from the sluggish propagation of neural impulses to the light-speed interactions of electromagnetic fields, combine in precisely the right way. The cosmic speed limit might not just constrain the flow of information, it might actually enable the emergence of subjective experience by creating the temporal structure necessary for conscious awareness. This would mean that consciousness is not separate from the physical universe, but deeply embedded in its fundamental structure. The same principles that govern the propagation of light across cosmic distances also shape the emergence of awareness in biological systems. We would be conscious precisely because we are part of a universe bounded by the speed of light, because we exist in a reality where information flow is constrained in ways that allow for the temporal integration necessary for subjective experience. And if this is true, then consciousness might be far more common in the universe than we currently imagine. Wherever information processing systems of sufficient complexity emerge, wherever the interplay between different speeds of information propagation creates the right kind of temporal structure, there might be the possibility for awareness to dawn. The speed of light would then be not just a physical constant, but a consciousness-enabling principle, a fundamental feature of reality that makes possible the emergence of observers who can contemplate their own existence. The cosmic speed limit would be essential not just for the preservation of causality, but for the very possibility of subjective experience. This brings us to a profound realization about our place in the universe. We are not separate from the cosmic principles we've been exploring. We are embodiments of them, living expressions of the relationship between information, entropy, and the speed of light. Our consciousness emerges from processes that respect these fundamental limits while creating something genuinely new and remarkable: the capacity for the universe to know itself. Every thought you think is shaped by the speed of light, by the electromagnetic interactions that bind your neurons together and enable the flow of information through your brain. Every moment of awareness is a temporary victory over entropy, a brief organization of matter and energy into patterns complex enough to sustain self-reflection. Every instant of conscious experience represents a local decrease in disorder that contributes to the universe's overall march toward maximum entropy. You are a walking, thinking example of how the cosmos can organize itself into structures capable of contemplating cosmic principles. The same fundamental forces that govern the expansion of the universe, the formation of stars and galaxies, the evolution of complexity from simplicity, also give rise to the neural processes that enable you to understand these very concepts. This is perhaps the most beautiful aspect of our cosmic situation. We are not external observers of the universe, but internal participants in its evolution. We are ways that the cosmos has developed to understand itself, temporary organizations of stellar matter that have gained the capacity for wonder, reflection, and appreciation of beauty. The photons that bring starlight to your eyes tonight have traveled across vast distances at exactly the cosmic speed limit, carrying information about the deep history of the universe. When that light enters your consciousness, when it triggers the neural processes that create your experience of seeing stars, the universe is quite literally observing itself through your awareness. This recursive quality of cosmic evolution, this capacity for the universe to develop observers who can contemplate universal principles, might be the most remarkable consequence of the speed of light and the increase of entropy. The same processes that drive cosmic evolution toward greater complexity have given rise to consciousness, to science, to philosophy, to the very capacity for wonder that allows us to appreciate the profound principles governing reality. And yet, for all our growing understanding of cosmic principles, there remain mysteries that challenge our deepest assumptions about existence itself. The more we learn about the universe, the more we discover how precarious our situation truly is. How many cosmic coincidences have conspired to create the conditions necessary for life and consciousness? The speed of light, the laws of thermodynamics, the fundamental constants of physics, all appear to be calibrated with extraordinary precision to allow for the emergence of complexity. Change any of these parameters by even small amounts, and stars might not form, heavy elements might not be created, planets might not coalesce, life might never emerge. This apparent fine-tuning raises profound questions about the nature of existence itself. Are we incredibly fortunate to find ourselves in a universe where the conditions are just right for complexity and consciousness? Or is there something deeper going on, some principle we don't yet understand that makes the emergence of observers inevitable? These questions become even more pressing when we consider the specific conditions that have enabled life to emerge on our particular planet. Earth exists in a narrow zone around the sun where liquid water can exist, but that's just the beginning of the cosmic coincidences that have made our existence possible. The size of our planet, the composition of our atmosphere, the strength of our magnetic field, the stability of our climate, all of these factors had to fall within incredibly narrow ranges to allow for the emergence and evolution of complex life. But perhaps most remarkably of all, there's one cosmic coincidence so improbable, so essential to our existence, and potentially so temporary, that its very presence challenges everything we thought we knew about planetary formation and cosmic evolution. It sits there in our night sky, seemingly innocent, casting its gentle silver light across sleeping landscapes and inspiring countless poems about romance and beauty. But that familiar celestial companion harbours a secret so profound, so statistically impossible, that its very existence should terrify anyone who truly understands the cosmic lottery that had to be won for us to be here at all. You see, our moon isn't just unusually large for a planet of Earth's size, it's impossibly, ridiculously, almost offensively large. Most planets in our solar system have tiny moons, if they have any at all. Mars has 2 pathetic chunks of rock. Jupiter and Saturn have dozens of moons, but even their largest are proportionally much smaller than ours. Earth's moon is so disproportionately massive that many astronomers don't even consider us a planet with a moon, but rather a double planet system. The Moon is about 1/4 the diameter of Earth and roughly 1/6 its mass. In cosmic terms, that's like a marble orbiting around a golf ball. No other planet in our solar system has anything remotely close to this configuration. It's as if nature violated its own rules specifically for us. But here's where the cosmic coincidence becomes truly unsettling. This impossibly large moon doesn't just hang there looking pretty. It's actively, continuously, and quite literally keeping us alive in ways that most people never realise. Without it, you wouldn't be here listening to these words. Earth would be a barren, lifeless rock spinning chaotically through space, and the entire story of biological evolution would have been over before it began. The Moon's gravitational pull stabilises Earth's rotational axis, preventing our planet from wobbling wildly like a spinning top that's losing momentum. Without this stabilisation, our seasons would shift dramatically and unpredictably. One year, the North Pole might point toward the Sun, creating extreme summers and winters. A few thousand years later, it might point in a completely different direction. The climate would fluctuate so wildly that complex life could never gain a foothold. But that's just the beginning of our lunar dependency. The Moon's gravity also drives our ocean tides, creating rhythmic cycles that may have been essential for the transition from aquatic to terrestrial life billions of years ago. Those tidal pools, alternately flooded and exposed, created the perfect laboratories for the chemical processes that eventually led to the first living cells. Even more remarkably, the Moon has been gradually slowing Earth's rotation throughout our planet's history. In the early days of the solar system, Earth days were only about 6 hours long. The Moon's gravitational drag has stretched our days to 24 hours, creating a rotational period that allows for moderate temperature variations and stable weather patterns. Without this slowing effect, our planet would experience extreme temperature swings between scorching days and frigid nights, making the evolution of complex life virtually impossible. And here's perhaps the most chilling aspect of our lunar dependence. The Moon is slowly moving away from us. Each year, it drifts about 3.8 centimeters farther from Earth. This might seem insignificant on human timescales, but over cosmic time, it represents a ticking clock counting down to the end of the conditions that make life possible on our planet. As the Moon recedes, its stabilizing influence weakens. Earth's rotational axis will gradually become less stable. Our days will continue to lengthen, and the tidal forces that help drive ocean circulation will diminish. In roughly 50 billion years, assuming our planet survives that long, Earth will become tidally locked with the Moon, showing the same face to its lunar companion, just as the Moon currently shows the same face to us. One side of Earth will experience perpetual daylight while the other endures endless night, creating conditions utterly hostile to life as we know it. But even before that distant future, the Moon's retreat threatens the delicate balance that has sustained life for billions of years. The question that should haunt anyone who contemplates our cosmic situation is this: how did we get so impossibly lucky in the first place? The leading scientific theory for the Moon's formation is almost as unlikely as its current existence. Around 4.5 billion years ago, when Earth was still a young, partially molten world, a Mars-sized object called Theia crashed into our planet in what scientists call the giant impact hypothesis. This collision was so violent that it vaporized Theia and ejected enormous amounts of material from both bodies into space. Normally, such an impact would either destroy both objects entirely or create a chaotic mess of debris that would eventually fall back to the surface, or drift away into space. But somehow, against all odds, the ejected material coalesced into a single, stable satellite orbiting at just the right distance to provide the stabilizing influence Earth needed. The precision required for this cosmic accident to work out in our favor is staggering. If Theia had been slightly larger or smaller, if the angle of impact had been different by even a few degrees, if the collision had occurred earlier or later in Earth's formation, if the debris had coalesced at a different distance, if any of dozens of other variables had been altered even minutely, we would not exist. Think about the statistical improbability of this scenario. In a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, and potentially trillions of planets, Earth appears to be the only world we know of that experienced exactly the right kind of giant impact to create exactly the right kind of moon, to enable exactly the right conditions for complex life. It's as if someone fired a bullet at a target from 1,000,000 miles away, while blindfolded during an earthquake, and somehow managed to hit the bullseye. The moon's existence represents a cosmic coincidence so unlikely that it challenges our understanding of probability itself. But the improbabilities don't stop there. Even after the moon formed, countless other factors had to align perfectly for life to emerge and evolve on Earth. The moon had to settle into an orbit that was neither too close, which would create tidal forces strong enough to tear our planet apart, nor too far away, which would provide insufficient stabilization. Earth had to maintain the right distance from the Sun, in what astronomers call the habitable zone or Goldilocks zone, where temperatures allow liquid water to exist. Our planet needed to retain a magnetic field strong enough to deflect harmful solar radiation, while allowing beneficial sunlight to reach the surface. The composition of our atmosphere had to evolve in precisely the right way to support life, without creating a runaway greenhouse effect like Venus or losing its atmosphere entirely like Mars. Each of these factors depends partly on the moon's presence and influence. Without our lunar companion, Earth's magnetic field might have developed differently. Our atmosphere might have evolved along a different path, and our position relative to the Sun might not have remained stable enough to maintain habitable conditions. The interconnectedness of these cosmic coincidences is perhaps the most unsettling aspect of our situation. It's not just that we needed one lucky break to exist. We needed dozens of lucky breaks, all of which had to occur in exactly the right sequence and maintain precisely the right balance for billions of years. Consider what this means for the possibility of life elsewhere in the universe. If Earth's habitability depends on having exactly the right kind of moon, formed through exactly the right kind of cosmic collision, maintaining exactly the right orbital characteristics for billions of years, then the number of potentially habitable worlds in the universe might be far smaller than we've imagined. This realization has profound implications for our search for extraterrestrial life and our understanding of our own cosmic significance. We might not just be alone in the universe. We might be alone because the conditions necessary for complex life are so incredibly, impossibly rare that they occur only once in trillions of opportunities. But there's another possibility that's even more disturbing to contemplate. What if the moon's formation wasn't a random accident at all? What if there's something about the laws of physics, the nature of planetary formation, or the structure of reality itself that makes such cosmic coincidences more likely than our current understanding suggests? Some scientists have proposed what's called the Anthropic principle, the idea that the universe appears fine-tuned for life precisely because we exist to observe it. In this view, there might be countless universes with different physical constants, different planetary formation processes, different cosmic histories. We find ourselves in one of the rare universes where conditions permit our existence simply because those are the only universes that can contain observers like us. This anthropic reasoning extends naturally to planetary formation. Perhaps there are countless solar systems throughout the universe, each with different configurations of planets and moons. We find ourselves on a world with exactly the right kind of lunar companion, not because such configurations are common, but because worlds without such companions never develop the conditions necessary for observers to evolve and wonder about their cosmic situation. Yet even this explanation feels unsatisfying when you consider the sheer number of coincidences required for our existence. The formation of our moon, the stabilization of Earth's climate, the development of plate tectonics, the emergence of life, the evolution of photosynthesis, the great oxygenation event that filled our atmosphere with breathable air, the survival through multiple mass extinctions, the eventual emergence of complex multicellular life, the development of intelligence and consciousness. All of these steps required not just favourable conditions, but incredibly precise timing and circumstances. It's as if the universe conspired across billions of years and countless variables to create the exact conditions necessary for beings like us to emerge and contemplate our own existence. The statistical improbability of this conspiracy is so overwhelming that it challenges our most basic assumptions about the nature of reality. Perhaps most unsettling of all is the realization that our cosmic good fortune is temporary. The same moon that has protected and nurtured life on Earth for billions of years is slowly abandoning us. Its gradual retreat represents a cosmic clock counting down to the end of the conditions that make our existence possible. In the short term, measured in millions or hundreds of millions of years, this retreat might actually benefit life on Earth by creating new tidal patterns and climate conditions. But over cosmic timescales, the moon's departure will inevitably lead to the destabilization of our planet's rotational axis, the lengthening of our days beyond what complex life can tolerate, and the eventual transformation of Earth into a world as hostile to life as Mars or Venus. This temporal dimension adds another layer of improbability to our existence. Not only did we need the right kind of moon formed through the right kind of cosmic accident, but we needed to evolve intelligence and consciousness during the brief cosmic window when that moon provides optimal conditions for complex life. We are living during a golden age of lunar influence, a period when our satellite is neither too close nor too far away, neither too stabilizing nor too destabilizing. In cosmic terms, this golden age represents a tiny fraction of Earth's total lifetime. The odds that intelligent life would emerge during this optimal window, rather than during the billions of years before, when conditions were too chaotic, or the billions of years afterward, when conditions will be too stable, are almost impossibly small. Yet here we are, existing precisely when and where we need to exist, contemplating the cosmic coincidences that made our existence possible. It's as if we won not just one cosmic lottery, but an entire series of cosmic lotteries, each with odds so astronomical that the probability of winning all of them approaches zero. This realization forces us to confront some deeply uncomfortable questions about the nature of existence itself. Are we incredibly lucky observers of a random universe, beneficiaries of a cosmic accident so unlikely that it borders on the miraculous? Or are we missing something fundamental about how the universe works? some principle or force that makes such coincidences less coincidental than they appear. The moon hanging in our night sky might be more than just a beautiful astronomical object. It might be evidence of something profound about the nature of reality, a clue that the universe is structured in ways we don't yet understand to permit the emergence of complexity, consciousness, and the capacity for cosmic contemplation. Or it might be exactly what it appears to be, an impossibly unlikely cosmic accident that happened to create the conditions necessary for our existence, making us the beneficiaries of the most extraordinary stroke of luck in the history of the universe. And so we come to the end of our journey through the cosmic speed limit, through the profound connections between entropy, light, and the very structure of reality itself. We've seen how the speed of light isn't just about electromagnetic radiation, but about the fundamental rate at which cause and effect can propagate through the universe. We've explored how entropy increase and the arrow of time are intimately woven together with this cosmic boundary, creating the temporal structure that makes complexity, consciousness, and wonder possible. The universe, it turns out, is far more interconnected than we ever imagined. From the quantum realm, where information becomes entangled in ways that respect causality while seeming to transcend space, to the cosmic scale, where black holes might encode reality itself on two-dimensional boundaries, everything is bound together by the same fundamental principle. Information cannot travel faster than light. You are part of this vast cosmic story, a temporary organization of matter and energy that has developed the remarkable capacity to contemplate the very principles that govern existence. Every thought in your mind respects the cosmic speed limit. Every photon that brings you the light of distant stars has traveled at exactly the same velocity for billions of years, and every moment of consciousness represents a local victory against entropy while contributing to the universe's grand march toward equilibrium. As you drift towards sleep tonight, remember that the same forces that prevent faster-than-light travel also make possible the complex information processing that gives rise to your awareness. You are both subject to cosmic laws and a walking miracle of their creative potential. Sleep well, dream gently, and until next time, may you always find wonder in the hidden connections that bind reality together.